And welcome back to the last video on another example of a multi-well system, essentially. And this one is for in situ remediation. So compared to pump and treat that we've talked about before, in situ again is the idea of in situ remediation is that we inject biological entities. So typically it would be like try and favor bacterial growth, for example, to remove some specific contamination. So let's say you have a carbon contamination, right? Some oil spill or some organic contamination, then of course, we can use organics to breathe essentially, or bacteria use it for energy, just like we eat food, right? Any kind of reduced carbon source is food for microbes. So if we keep microbes happy, then we can remove the oil. But of course, the microbes need other sources of nutrition. So maybe they'll need, some nitrogen for their protein. So maybe we need to add nitrogen to the aquifer, or phosphorus, so on and so forth, right? So other nutrients, for example, to keep them happy and favor their growth. So again, this is another way of cleaning up a site, is to essentially do an in situ remediation where we control what's going on with wells around the site, but instead of pumping the water out, treating it, and discarding it, or discarding the clean water, now we're trying to actually, clean it in situ. And the example I want to show is a sort of a more advanced, almost setup. So far we've seen essentially well pairs. In the last lecture on the capture zone, I showed you how you can design like for several wells, 2 and 3 wells that do the job of one essentially. So we limit the drawdown, so it doesn't draw down as much. Here the idea is to isolate the contamination, real good with essentially a 4-well system instead of 2. And I think this is an interesting, concept, because really you can see the difference here. So here, let's say you have 2 injection wells. These are the black ones. And then you have 2 extraction wells. These are the white ones. And the advantage is that if you have an injection and extraction wells that we've seen before, you get that inside cell here. But the problem is there's still some diffusion on the edges, right? So if you're trying to contain pollution that is, inside this zone here, right? The two well system is good, but is not perfect, right? There's always going to be some diffusion out of that cell. Now, what's interesting with this paper here, the Liu et al. 2006, is that you add another outside pair of wells, which are here and here, essentially, right? Which then re-isolate this outer ring, essentially, right? So you're isolating the pollution inside the first 2 wells, your extraction and injection wells, and then you're isolating an extra ring, on the outside with another pair of wells that are really there just to sort of safeguard the environment around. And then you can kind of keep this isolated for, many years, or however long you need to get that in situ remediation working. And here are, just again, using my little Excel, find a difference version, you can see how that would work. And this is just plotting the flow lines of this system here, right? The 2 wells, the 4-well system, just using MATLAB to plot it. And you can really see how this inside cell is completely isolated thanks to the outer 2 wells, right? Completely isolated from the environment. So there's really no chance of polluting the environment, because again, the outer 2 wells really are completely isolating this inner cell. Compared to a 2-well system, right? Following advantages: the inner cell is separated from the original flow by the protective outer cell. The recirculation ratio in the nested inner cell is less sensitive than the 2-well system. So this recirculation ratio again is important for a remediation or an in situ, system, because you're injecting and extracting, right, water so that you can replenish the zone in, let's say, nutrient, like I explained, or whatever it needs, right? So having a faster recirculation ratio is actually interesting, so that you can, again, you can enhance, right, the remediation, or you have more turnover time in there. Again, the average residence time within the nested inner cell can easily be adjusted by changing the pumping rates of the well. So again, that inner cell is completely independent, basically, of the environment, and you can really play with it. So again, if you need, more time for bacteria to process something, for example, you can kind of slow down the recirculation, or if you need, less time, right? If you need to inject, let's say, a nutrient real fast, then you can accelerate the pumping and rate, and without any interference with, the outer environment. So a really neat sort of system that was developed, or the experiments from this paper, and again I'll put it online, were done at Oak Ridge, where all the nuclear storage. There's a lot of basically groundwater issues down there because of all the nuclear tests and nuclear storage that they had down there. Okay, I think this is it. That's all I want to say about in situ remediation. That's a whole topic in and of itself. But again, I just wanted to show you that sort of 4-well system where you can really see, how flexible essentially well systems are for environmental engineering, and how we can kind of design pump and treat or in situ remediation systems that would, isolate a pollution and allow us to treat it. Thank you.